back. So we have the last speaker of today, who is Pietro Freni from the University of Leeds. So thanks for joining us. And he'll be speaking about what should strong vector spaces be. So please take it away.
Thank you for inviting me and taking this conference. I'm not a category theorist, but I mean, I happen to need to use some category theory in what I was doing, and I will talk a bit about this. So in the field I was supposed to work at the beginning of my PhD, there are some questions involving this notion of strong linearity, which appears in the literature, let's say, around generalized power series and alike. And the problem I had when investigating this question is that this notion was in the literature more an observed phenomenon and was given ad hoc definitions in contexts in which you had much more structure, which you ended up using in the end in the results. So whence the question of the title of this talk: what should strong vector spaces be? So what if you want to study strong linearity, what is the natural ambient category to do so? And so what I'm going to do in the next 20 minutes is to talk you through the application of some standard tools of category theory to discuss and describe the possible answers to this question. Then the point will be that once you have a setting, you can work with it and then I present some results. But the main point of the talk will be to get to the setting. And yeah, so let us start to give you some context and then also present some motivation with the first basic answer to this question. So, which is the category of base strong vector spaces. Now, every time in the literature one talks about strong linearity, it usually is in a specialization of the following context. So you have a field K of coefficients, a set gamma, and then an ideal of sets of parts of gamma, which contains the ideal of all finite subsets. Then you consider the set of functions from gamma to K whose support is in this ideal F. The support of a function, of course, is the set of elements at which the function is non-zero. Now, this is a sub-vector space of K to the gamma with the termwise sum, just out of the fact that F is an ideal. To bring this to a familiar ground, here are two basic outcomes of this construction. So if you take the finite subsets as your ideal, then you get the canonical construction of the free vector space over gamma. And if instead you take the full ideal of all subsets, you get K to the gamma. Then you usually think of gamma as naturally included in this vector space, and you identify every point of gamma with the function which is 1 at that point and 0 everywhere else. And then you think of elements in here as series with coefficients from K and monomials from gamma. And this is just a constraint of on the supports. And let's say a justification to do so, to think of this as series, is that in this context, you can make sense of some infinite sums. Namely, if you have a family which happens to have the property that the corresponding family of supports is locally finite, which is this condition here, then you can define the termwise sum, even if the family is infinite, for the very simple reason that above every point of gamma, you see a family of elements of K, which are non-zero only for finitely many indexes. So the sum makes sense, at least in K to the gamma. And then if your family has, moreover, this property here, that is that the union of the supports is still in F, then you're sure that the result is going to be in this vector space. And so you take this as definition of summability for a family. And you say, and to summable families, you associate sums in this way. Okay, now that you have a recipe to build vector spaces with additional structure out of this starting data, you can say that a linear map between two vector spaces of this form is strongly linear if it preserves summability, so it sends some summable families to summable families, and it preserves the sums of the summable families. And you can call this the category of base strong vector spaces. Okay, and I'll denote it by this P sigma vect for the rest of the talk. So before proceeding any further, let me tell you, let me give you a taste of what are the applications and what is the context where these things arise. So if you have a total order on gamma, and you consider an ideal of subsets which is containing the ideal of well-ordered subsets of gamma, then this vector space has a natural valuation, which is given by this formula. You just take the minimum of the support of an element. If you don't know what a valuation is, it's a sort of thing that behaves as the order of a Lorentz series or as minus the degree of a polynomial. Okay. The point is that within valued structures, one it is custom to consider to study this as a particular class of extensions, which are called immediate extensions. And people are particularly interested in maximal immediate extension, which in category theoretical terms means essentially objects which are injective with respect to this class of maps. And this construction, specifically with this ideal of well-ordered subsets, is usually injective, and it allows you to describe injective halves of objects. Okay. Both as a way of giving a weak application of strong linearity, and also as a way to bring some more familiar examples into the picture. Let me tell you that if gamma is an linearly ordered abelian group, then this vector space can actually be endowed with a unique product, which extends the product on gamma along the natural inclusion I told you before, and which is strongly linear in both arguments. This is called the Ham field with coefficient from K and monomials from gamma. Now, the two familiar examples I'm going to give you are essentially, if you take gamma to be a multiplicative version of the additive group of integers, then you get your familiar field of Lorentz series. And this is maybe a more interesting example. If your group is a multiplicative version of the additive group of rationals with the usual order, and F consists of the well-ordered subsets which generate a finitely generated subgroup, then the resulting field is what is called the field of Puiseux series, which is, if you know what it is, the Henselian closure of the field of Lorentz series. But if you don't know what Henselian closure means or what Henselian means, don't worry. Assume K is algebraically closed, then this is actually the algebraic closure of the thing above. Okay, so this gives you some motivation. So I already gave you an answer to the question, a possible answer to the question of the talk, of the title of the talk. So in order to proceed, I should at least tell you why you may not be satisfied with this answer. So there's various reasons. One has to do with quotients, but I don't want to expand on that. And the other one, which I'm going to give you for this talk, is that the definition is ugly, in that it is parametric. It gives you RSI to build objects instead of telling you they are structures satisfying some axioms. It's a bit like if instead of defining the category of vector spaces, I would define the category of base vector spaces like this. So the objects are the canonically built free vector spaces over some set, and then as arrows, I just take all the linear maps between these. Now, if you have enough choice in your set theoretic universe, this is equivalent to the category of vector spaces, but this is not how you define this. How do you define the category of vector spaces? Now, I do not have a description of a category, a nice description of a category which is equivalent to the category of base strong vector spaces I gave you at the beginning, but I have it for some special and particularly relevant full subcategories. Well, one is this one, but this is not too interesting. This is already a full subcategory of the category of base strong vector spaces. Just take always the ideal to be the ideal of finite subsets. But the interesting point is if you consider the full subcategory on object of the form k to the I, because as you may reckon, this is actually isomorphic to the dual of the free vector space of I, and the map between spaces of strong vector spaces of this form is strongly linear if and only if it is the dual of a map on the corresponding free vector spaces. So in more category theoretical terms, this tells you that this assignment here is a fully faithful k-additive functor from the opposite category of base vector spaces to the category of base strong vector spaces. And why is this more interesting? Well, essentially because it allows you to describe this additional structure, because a family will be summable if and only if it is the image of I as seen as in k to the I for a unique strong linear map. And if you think carefully about this, but I'm asking to believe me here, this actually tells you that this functor is dense. Okay. And so I usually denote the copies of elements of I in k to the I with this little delta I, because they're essentially connected deltas. Before going to the next slide, since it's going to be relevant in parsing it, I want to remark that these elements correspond to the ith selecting coefficient functional from the free vector space over I to k with the canonical isomorphism between this and this. Okay, so if you want to give another definition of category of strong vector spaces, what should be a reasonable one? So we wanted to contain the category of strong vector spaces of the form k to the I, and we want to describe sums and the additional structure in the same way. And also we are just interested in determining categories up to equivalence, so we can just switch from the opposite category of base vector spaces to the category of the opposite category of vector spaces. So you define a reasonable category of vector spaces to be a fully faithful k-additive extension of the opposite category of vector spaces with some properties which you want out of it. So you want every object to have an underlying vector space, and you want this to give you a faithful functor. And the underlying vector space you want to be essentially a set of maps from the vector space K. Then you want the same slogan about summable families and summability to hold. And this essentially amounts to require that this map is one-to-one, and that the families, this is the underlying vector space of X, the families in X, which indexed by I, which are deemed to be summable, must be the one in this image. So this is the objects you kind of think as k to the I, okay, with respect to this embedding. And then with this understanding of summability and sums, you want that a map of the underlying vector spaces actually comes from a map in the category if and only if it preserves summability and sums. Okay, and so this actually tells you that these conditions actually imply these three conditions on the functor iota. Okay, iota must be dense, and this is the most substantial part. Then this is just the first condition in the previous slide, and this is part of the second condition, that this must be one-to-one. And it actually happens that these are actually equivalent if you give the right meaning to summability and sums. I mean, you just give the one you agreed to give. And also you want the category C to be locally small, because it makes sense to give the definition like this. And so you take this as a definition of reasonable category of strong vector spaces. Okay. And of course, the category of base strong vector spaces will be a reasonable category of strong vector spaces. Now, for honesty, I need to tell you that A2 is redundant, even if it's not so clear from how it's written, it's not too difficult. But the point, which is, as you may have guessed, more worth focusing here, is of course that iota is dense, because this automatically tells you, out of basic theory of dense functor, that C is equivalent to a full subcategory, of course extending the subcategory of representables, of the category of functors from vector spaces to vector spaces, which are k-additive, and the natural transformation among them. Okay, so why so? Well, essentially the usual theory tells you that if you post-compose this with the forgetful functor and end up in the presheaves on the top, this is iota is dense if and only if this composition of functors is fully faithful. But out of the fact that this is faithful, you get that this must be fully faithful also. Okay. And yeah. So up to, without loss of generality, we can think that up to equivalence, a category of strong, reasonable category of strong vector spaces is a subcategory of this category here, and that iota is the Yoneda embedding. Okay, now if you look at the condition, now let us analyze the condition 3, and let us see in this context. So the domain of the map we want to be monic is going to be equivalent to the natural transformation from the ith power of the identity functor to x. And the codomain is going to be equivalent to the natural transformation from the ith copower of the identity functor of x. And the map is going to be actually just the natural transformation to x applied to the natural inclusion of the copower into the power. Okay. And I mean, this is an abelian category, and this is essentially, so A3, what A3 tells you is that every object must satisfy this condition. So the natural transformation from the cokernel of this inclusion to x must be 0. Okay. And then you can check that the category of such functors actually satisfies, is locally small and satisfies all the nice properties you need. So what you actually have proven, if you believe me when I tell you that A2 is redundant, is that you found a maximal reasonable category of strong vector spaces, or a universal one, if you prefer, which is up to equivalence this one. Now, this is, let's say, the most general answer you can get. You can call it the category of all strong vector spaces. Now, is this a satisfying result? Well, not so much, because this is not a very nice abelian category. Essentially, if you're not careful with the foundation, this may not even make sense. Okay, but so I need to be like clear on what are my foundations. So I'm essentially working in ZXC, and I'm assuming the existence of a non-trivial Grothendieck universe, or equivalently of a strongly inaccessible cardinal. And then when I say vector, I mean the small vector spaces. And when I say small, I mean something which is in the Grothendieck universe. Everything outside I deem to be large. Okay. So vector is the category of small vector spaces, and card is the small cardinals, and set is the small sets, and the usual conventions. So this category is not locally small. Okay. And of course, just out of the fact that by definition, this is a right orthogonal class, a right orthogonal subcategory, you get that this is closed under limits, and this is small complete. So your category will have all small limits, but there is not much you can say about colimits, because you in principle you would like this to be a reflective subcategory, and if you are in here, it's hard to do. It's hard to show this a reflective subcategory. In fact, what happens is that just out of the fact that X satisfies this condition, X must be a small functor. It must be a small colimit of representables. So in fact, the category up to equivalence is the category of ind objects of the top. Now, the small colimits in the previous category is not the official definition of the indization of vectop, but it is really the same, and you can check it if you just think that the forgetful functor from vector spaces to set creates filtered colimits. So once you have this, just out of the fact that every object in here is lambda presentable for some small lambda, and that this category is lambda small, you get that this is actually a reflective subcategory. So you go through your universal category as essentially as a full as a torsion-free path for a particular torsion theory of a B-complete abelian category. Okay, so now you have a context, and it's not even that bad to work with strong vector spaces. So there are some questions which one can address in this, and there are some other slides which are about the question I addressed about this. They contain much more information than I want to present. They are there just in case there are specific questions, and I don't need to write too much on the slides. So the first problem I considered, which okay, no, there is another thing. I wanted to give you an outline of the proof of the fact that every functor satisfying this condition is actually small, and so the way you prove this is you consider arity of functors, which you define like this. You say that a functor from back to back is actually lambda if it is a left-hand extension of a k-additive functor defined on the category of vector spaces of dimension less than lambda, where lambda is a small cardinal. Then you observe that X is small if and only if it is lambda for some small cardinal lambda. Now, this notion has a quite practical interpretation in terms of elements of sigma vector of the category of all strong vector spaces as defined first. In fact, a functor is lambda if and only if every summable family has actually a support which has cardinality less than lambda. And then with a very simple pigeonhole argument, you can actually show that every functor satisfying that condition, which is a strong vector space, is actually it has actually arity less or equal than the successor of the cardinality of its underlying vector space. Okay, it's probably not a good bound, but maybe it is optimal for high enough cardinalities, for high enough arities with respect to the cardinality of the base field. So yeah, about the work you can do on this. So one question I had was about the reflection. Okay, I wanted to have an explicit description of the reflection as a transfinite construction, and this is related to the problem of building the smallest. So you have a base strong vector space, you have a linear subspace, and you want to build the smallest subspace which is closed under infinite sums. So you take all the possible infinite sums, but this may still not be closed, and you want to know how many times you have to iterate. And this is related to the transfinite construction of the usual last transfinite construction of the iterator. So how do you build the reflector? How do you build the reflector in this sort of situation? Usually, so you start with a well-pointed endo functor, which you could think as a naive reflector, okay, and it is not the actual reflector, and you iterate it until you get something which is stable and which is in the category you want to reflect in. And you need to perform the construction, you need some co-completeness, and then to make so that the construction finishes, you need that your functor is in some sense accessible with respect to some cardinal. And so there is an easy bound. If X is lambda, then after lambda many iteration, you're already there. This is not particular, but I wanted the optimal number. And in fact, this is not optimal, at least if X is Aleph quanary, so if it has arity Aleph 1, then the naive reflector is already good. Okay. And this has to do with this combinatorial lemma, which holds only for countable dimensional vector spaces. And this lemma in particular, not the theorem, but the theorem I don't know if it's false for higher cardinalities, but this lemma is definitely false for a higher for more than countable cardinalities. So you want, well, the motivation for studying strong linear structure is that you usually have much more structure. So you at least want a monoidal closed category, and you have it. So InvecTop has a natural monoidal closed structure, which is induced on it by the one you have on the opposite category of vector spaces. So this is the definition. And the cool thing that they both restrict to this category of strong vector spaces. I mean, the fact that this restricts is not so surprising, of course, but the fact that this restricts has to do with the homological properties of the things which respect of the generators of your torsion class, essentially. So, and finally, I gave you two answers to the question of the talk, which gives the title of the talk, and I gave you the basic one, or the base one, if you prefer, and I gave you the most general one. Now, there is also a more natural one, probably, which is you can actually there is a reasonable category of strong vector spaces, which is actually a category of topological vector spaces with a linear topology with some additional properties. And these additional properties are essentially that they are topological union of their linearly compact subspaces. Okay, and this relates to this old theorem of Lefschetz. Okay. Yeah, there are much more, as I said, there are much more information in these slides, but I didn't want to spend too much time on this. Finally, I have some questions left. So the category I have this natural answer to the question, the category of this topological category of strong vector spaces. Well, it is properly contained in the full in the category of all strong vector spaces, so that they are not equivalent. There is something which is in the bigger one and not in the smaller one. But I do not have a separating example between the category of base strong vector spaces and the topological one. Yet all of these are all the base ones are topological, but I don't know the other way around. I strongly suspect not, but I couldn't produce a counterexample. Then it would be also nice to know whether this is reflective. And this seems kind of weird because it has a weird description. And now this is kind of what motivated the whole analysis at the very beginning. I wanted a strong linear version of the color differential of a Hahn field, of this Hahn field in particular. And I kind of showed they exist once you have the monodal closed structure and not the nice completeness and completeness properties. It's fine, but I do not have a nice description, and I couldn't disprove that the strong linear color differential you get, for example, as a description like this. And finally, so sigma vector is a torsion-free part of a torsion theory on the abelian category of in the top. And actually, I didn't look at the torsion part. Maybe it isn't. I don't know. And yeah, this is the last slide. No, this is the last slide. Thank you. And all the things I said, which are kind of new, not the obvious one, are actually not peer reviewed. So, I mean, there is a chance there are mistakes. I think not, but who knows? And then there is another reference here. Yeah, the work is in a preprint on the archive. And then this other reference here is the oldest one I could find in which strong linearity is kind of treated as a thing, even though in a very special context. There is also a thesis, which is around the same years, which is a definition, but it's not published, so I couldn't actually give it here. And that's all I wanted to say. Thank you.
All right. Thank you very much. Let's thank the speaker for the very nice talk. Okay. So does anybody have any questions or comments about this work? Again, raise your hand. Okay, I see Ivan has one. So please.
I have many. I'm happy to be the last one if there are other people.
Okay, let's see if there's someone else who's maybe a bit shy and wants to go. Just waiting for the moment.
I have a question.
Please.
Pietro, could you give us an idea of why topological vector spaces were not good enough for you to do what you wanted to do?
So let me go to the slides. So the slide about topology. So and strong vector spaces are I mean, essentially the point is that you're working in a context in which you're just interested, you build everything just out of these infinite sums. Okay, and one way to understand this category of strong vector spaces is a bit like if you have a category of topological vector spaces, but you just want so this the reasonable category of strong vector spaces I give you is not the whole category of topological vector spaces, morally, it's just the ones for which in which the topology can be described in terms of some special nets, okay? And these nets are essentially the nets you get as finite partial sums of a certain family, okay? This is kind of the content of this topological version of the thing. And yeah, if you're working in a context in which you just work with these sums, it's yeah, the category of topological vector space is also not so nice in general. At least the one with a linear topology, because the field has no topology. So one you want to consider is usually you think of the field as discrete, and then you consider topological vector spaces over that, and that's not a nice category. I hope this is a bit nicer. At least yeah. That I don't know if this answers your question. Probably the idea I'm trying to convey is it seems the natural operation is these sums in the context they are working in, and topology is a bit too wild for it. Also, the sums are already oblivious with respect to some things in the applications, because evaluation is not really a topology. It's something, in some sense, it's a family of topologies. Okay.
Okay, thanks.
Okay, so Ivan, I guess you can go if there's no one else waiting.
Okay, so my first question is, so the first time I saw this Lefschetz theorem, it was in the context of my paper about codensity monads. And so for this reason, okay, I cannot explain why this is the reason, but okay, it doesn't matter. Did you think about the option that the kind of objects you are studying are actually internal vector spaces in the category of condensed sets?
I do not know what a condensed set is.
Okay.
Can you give me a definition?
It's a kind of category of sheaves over a site, and the site is the site of, if you want, profinite sets or something like that, or a very close friend of that. The reason why I'm saying it is that the topology that Lefschetz should give you is a very profinite topology.
Yeah,
this is not true, but kind of true. And so maybe what you're looking at are some kind of internal vector spaces in this very big category where sets are, where objects are gluings of profinite stuff. This is just something I would consider.
Right. Yeah, I think yeah. So yeah, it could be the case. So one thing is that I think that probably just the strong linear structure is not enough for the applications, because if you want to apply to as I was saying, if you want to study evaluations, evaluation is something more than a topology, because you can think of linearly topologized topological vector spaces sort of as objects in provect, sort of. They are happy supplemented provector spaces. But evaluation is not just a linearly topologized vector spaces. It's if you want, it's a topological vector space in which you have a family of topologies. It's
a Frechet-like object.
Yeah, it's like if you have a topology of topologies. In fact, you talk about pseudo-convergence. It's like a pro object, something like this. But there are some technicalities, so it's not really just an intro object. I mean, this is one way to understand it if you want to formalize it as they formalize provector space, as they formalize topological vector spaces in terms of functors. I don't know if what I said makes sense. Like I can elaborate more if you want. I can write something.
I would send you messages after this seminar.
Okay.
I have another comment. So because you are interested in the color story, and in general, you're interested in understanding differential structures. In category theory, there is this notion of tangent category, which amounts to develop a kind of tangent space construction over category of spaces. And I mean, it could be the case that you have such a tangent structures, and for those structures, there is already a lot of mathematics that allows you to do up to PDEs even. So like you really have a lot of things there. And then the last comment, which is connected to my previous one though, is so in cohesive mathematics, so Matthias is here, so I shouldn't say it maybe. There is in axiomatic cohesion, there is the notion of a concrete object. And maybe your category of how do you call it? I forgot the name.
Strong vector spaces.
Yes, maybe they are concrete objects in the category you are studying. I forgot the names, so I cannot say names. You said I would like to show this is reflective. I don't know if it is reflective.
No, it is reflective.
No, not this one. No.
No. Okay. These ones. Okay, I see. You mean the based ones, the one
exactly.
you build out of this construction.
Exactly. Yeah. So maybe the based ones could be concrete objects in your category. This is a possibility.
Okay, so I need to have some note of what I need to check. So
I will send you messages.
Okay.
Okay.
So it's cohesive mathematics, and I need to look at concrete objects.
I will send you messages.
Okay, thank you.
Okay, thanks for the nice discussion. Is there anybody else that wants to chat or have a comment about this talk? Okay, if not, we thank the last speaker of today for a very nice talk and discussion. Thank you, Pietro. And we remind you that there's going to be another session of the Ithaca's Fest. It's going to be on the 16th of June, so you can find everything on the website. We will have Enrico Vitale, Julia Ramos Gonzalez, and Andrea Cappelletti. So you're welcome to come back, and you're welcome to stay here if you want to have a chat or just simply say hi. So thanks to all the speakers, and we'll see you next month.